Hello and welcome to another physics lesson. Today we are looking at radioactive decay with a focus on half-life and decay constant. If you have been following this series, you will remember that in one of the classes we had, we looked at radioactivity. We defined radioactivity, defined ionizing radiation, background radiation. So now we are looking at radioactive decay, looking at what half-life and decay constant mean. By the end of this lesson, you should be able to define and explain half-life of a radioactive element, define decay constant, calculate the half-life of radioactive substances, mention the applications and dangers of radioactivity, and mention two instruments used to detect radioactivity. Let us start by defining what half-life is. Now, radioactivity is not affected by temperature, it's not affected by pressure or other external factors. It is random. So when something is random, it means that you cannot actually predict what will happen. So no specific atom can be predicted to disintegrate at a given time. Now, each radioactive element disintegrates at a specific rate peculiar to it. This is characterized by its half-life. What then is a half-life? Half-life is defined as the time it takes for half of the atoms in a radioactive element to decay. That is the amount of time it takes for a radioactive element to decay by half of the original atoms in the element. If, for instance, an element has a half-life of 10 years, it means that it will take 10 years for the number of atoms in the element to reduce by half, and another 10 years for the remnants to reduce by another half of it, and so on and so forth. So when an element decays by half its original number of atoms, the remaining half does not disappear in the next half-life. I have to stress that. Rather, the remnant also decays by half in the next half-life. And this process continues infinitely. If we have 200 atoms, for instance, in a radioactive element, initially with a half-life of 5 years, after 5 years, half of 200 will remain, that's 100 atoms. After another 5 years, not that the whole remaining 100 will go off, no. Rather, half of the 100 that was left will remain, that's 50. And then after another 5 years, half of 50 will remain, that's 25. And then on like that. That means that after another 5 years, half of 25 will remain, that's 12.5. That is what will keep happening infinitely. Here we have two pictures. One of them shows the decay curve. We can see for cobalt-60, for instance, you can see how it continues to disintegrate every half-life. One half-life of cobalt-60 is 5.27 years. So that means that it will take 5.27 years for 10 grams of cobalt-60 to reduce to 5 grams. Another 5.27 years for 5 grams to reduce to 2.5 grams. And then another 5.27 years for 2.5 grams to reduce to 1.25 grams, and on like that. So we can use a decay curve to deduce the number of atoms that will remain after a certain half-life, after maybe 3 half-lives or 4 half-lives. On this curve, for instance, we have 5 half-lives. So after 5 half-lives, we can deduce the number of cobalt-60 that will remain by just tracing the point on the curve to the y-axis. On the other picture, we can see an example of an artificial radioactive process where a neutron is bombarded with, a nitrogen atom is bombarded with a neutron, and then it forms carbon. Ordinarily, nitrogen atom is stable, but by the time you bombard it with a neutron, it becomes unstable, and then a carbon atom is formed. That's an artificial process of radioactivity. Let us go on by looking at the decay constant. The decay constant. The rate at which radioactive elements decay is proportional to the number of atoms present. I say again, the rate at which radioactive elements decay is proportional to the number of atoms present. And in physics, we already know that when we hear rate, we are talking about time essentially. So rate of something means that thing over time. So rate of decay of radioactive elements means the number of elements over time. The change in number of elements, that's the n, over change in time, the t. And that is proportional to the number of atoms present. That is the proportional to n. N is the number of atoms. The n over the t is the rate of decay. The minus sign indicates that n is reducing with time. So that change is actually a reduction. That's why we have negative signs. It's like I'm talking about deceleration under mechanics as against acceleration. Deceleration is a reduction in the speed, so it carries a negative. So in this case also, we are talking about a reduction in the amount of atoms present. That is why the negative sign, the minus sign is there. So if you remove the proportionality sign that we usually do whenever we have variation, the n, the t will be equal to minus lambda n. Lambda is the decay constant we have introduced after removing our proportionality sign. If we make lambda the subject of that formula, we will find that lambda will be equal to minus 1 over n bracket the n over the t, rate of disintegration. So that means that decay constant is defined as the instantaneous rate of decay per unit atom of a substance. Per means division. So rate of decay, that's the dn over the t. The n divided by the t divided by the number of atoms also. That's why we have the n over n dt. Or we can just say that the decay constant is the number of atoms disintegrating per second, which is what the n dt is, divided by the number of atoms in the source at that time, which is what n is. If we do some integrations and logarithm of this equation 1, we will find that our t, half-life, is given by 0.693 over lambda. So whenever you are given a decay constant, and from there you are asked to find half-life, or vice versa, all you just need to do is to use this formula, t equals 0.693 over lambda, where t is the half-life, lambda is the decay constant measured in per seconds. It's possible to be per year depending on the question. Some questions will decide to give you per minute, but the SI unit is per seconds. Let us see some solved examples. We have a radioactive element with a half-life of 10 years. So how many years will it take to lose 3/4 of its original value? Essentially, we are asking you how many years it will take for the radioactive element to have 1/4 of its initial value left. I mean, when you lose 3/4, that means you have 1/4 left. Now, if the half-life is 10 years, that means that after every 10 years, half of the previous number will remain. So if the initial number of atoms is n, since we are not given a specific number, let's say it is n. After 10 years, what will be left will be half of n. That's n over 2. After another 10 years, what will be left will be half of n over 2. That will be n over 4. That means that it will take it 20 years for the element to have 1/4 of its initial value left. That means it has lost 3/4 of its initial value in 20 years. Another example is to find the half-life of a radioactive element. We were given decay constant here. So we just use the formula 0.693 over the decay constant 200 and we get the half-life. Now we have another one. A substance has a half-life of 3 minutes. After 6 minutes, the count rate was observed to be 400. What was its count rate at 0 time? We have to be careful here. The 400 is not the original value of the number of atoms. The 400 was the value that was left after 6 minutes. Now remember that 3 minutes is the half-life. So 6 minutes is 2 half-lives. So after 2 half-lives, what was left was 400. So that means that after one half-life, there will have been twice of 400 left. So twice of 400 after 3 minutes will have been 800. Now the question asks for count at 0 time. That's at the beginning at 0 minutes. So that would have been a double again of the value you have at the first half-life. That is 800 times 2. So essentially, you are given 400, which is the value after 2 half-lives. And you are looking for the value when it had not started disintegrating. That means this value of 400 you have, you must double it 2 times. Because after 6 minutes, there were 2 half-lives. So you must double it 2 times. That's why we have 400 times 2 as a count rate at 3 minutes, and then 800 times 2 as a count rate at 0 time. So the answer is 1,600. Now let's look at some applications of radioactivity. Ionizing radiation can be dangerous, but it still serves many useful purposes. It is used in cancer treatment, for instance. Gamma rays are used in cancer treatment, though they can damage healthy cells too, so a lot of precision has to occur when it's being used. It has to be precise, and the doses have to be accurate, well measured. Radiation is also used to sterilize medical equipment in a process called irradiation. Food products are also preserved from bacteria by irradiating them, even though this is not a widely used procedure because of public safety concerns. We also have radiation used in carbon dating. Carbon dating is a process that is used to date archeological specimens and rocks. We know that every specimen, every rock, every plant has carbon deposits on it. So under carbon dating, the amount of carbon remaining on it is calculated, and then knowing the decay rate of carbon, we can now deduce that, okay, how long would it have taken for this amount of carbon to be deposited on this material? And that's how they are able to get the age of an archaeological specimen or rock. Carbon dating is basically about getting the age, getting how long a particular specimen has been around for. Gamma rays also used, like X-rays, to view contents of luggage at airports in a process called gamma radiography. We also use gamma radiography to check for imperfections and leakages in welded joints and metal casings. When you have a metal casing, and you are not sure if it's leaking or not, you don't know if it's leaking or not, all you need to do is to send gamma ray into it. And even in the tiniest of holes that you have there, gamma ray will escape from inside. Then you know that it's leaking. Now, radiation is also used in medical tracing. That's a system used to detect abnormal cells in the body. For instance, iodine tracers may be used in the body to detect how the cells in the body react, so that they can know which cell is damaged or which cell is still good. And as I said earlier, radiation has its dangers. Alpha radiation is dangerous if the source is inside your body, because it will be absorbed by cells in the body. Beta radiation can penetrate the skin, so even if the source is outside, it can still penetrate the skin and cause danger. Gamma radiation can be absorbed by any cell, so it can cause mutation. However, because it is weakly ionizing, it can pass straight through the body without causing harm. So it has useful benefits, and it can also cause harm. To detect ionizing radiation, therefore, what is used? We have a photographic film which scientists wear when they are working with radioactive materials. When the film becomes fogged, it shows that the scientist has been exposed to a certain amount of radiation. The measurement of radiation, measurements can be done based on the fogginess you have on the film. So there's a range. It will tell you can measure, if it gives you a particular reading, you know that you have had this amount of radiation, and on like that. But a very popular instrument used in industry is the Geiger-Müller tube. The Geiger-Müller tube. This is a glass tube with an electrically conducting coating on the inside surface. So when radiation enters the tube, it causes low pressure gas inside to form ions. These ions will then send a pulse of current to flow from the electrodes to the conducting layer. This can then be detected by a counter that is attached to the circuit. So this counter now counts the amount of radiation a person has been exposed to. These are not the only instruments used to detect ionizing radiation. You can find out more by yourself. Now we have the circuit and diagram of what a Geiger-Müller tube is. We have the battery supply, we have the insulator, we have the metal casing I mentioned earlier, and then we have the counting circuit that will be connected. The counting circuit is connected to the Geiger-Müller tube, and then measurements can be taken from that. So we have a homework also. That's where we'll be rounding off. Describe 2 uses of radioactivity in medicine and industry. When I was talking about applications of radioactivity, I listed all of them. So I want you to now look at them and mention 2 and explain them. 2 in medicine and 2 in industry. And then write an equation to represent the decay you have in question 2. So this is where we end the lesson today. I hope to come across to you in another interesting lesson, interesting video. Do not forget to leave comments. If you do have a question, do not hesitate to ask in the comment section on this YouTube page, and I'll get back to you. Once again, the YouTube name is David Oluwadara. Subscribe and like our videos. Thank you.